Retrieval always seems to force a painful choice. A bi-encoder crushes each document into one vector, which is blazing fast to search but loses all the fine detail. A cross-encoder reads the query and document together, which is beautifully accurate but far too slow to run over a whole corpus. For years those felt like the only two options. Then along came ColBERT with a genuinely clever middle path, one that keeps a vector for every token and matches them at the very last moment. Nearly cross-encoder accuracy, close to bi-encoder speed. Let us unpack how it pulls that off. So where exactly does this middle path sit? Here are the two extremes side by side. Squashing an entire document into one dense vector is the bi-encoder's whole trick. Because that vector never depends on the query, you can pre-compute the corpus and search it in milliseconds. The catch is resolution. Compress a long passage into a single point and the fine signals that decide a truly close match simply wash out. Here the document becomes many vectors, one per token, computed offline just like before. The query is encoded into its own per token vectors too. Matching then happens late and cheaply at search time, comparing tokens directly, so it captures much of the precision a cross-encoder gets from reading both texts together. So how does the scoring actually work? Token by token. Watch the maxim operation. First, offline, encode the document into one vector per token. Every word, in effect, gets its own little embedding rather than being averaged away into a single document vector. This is the pre-computed side, done once and stored, exactly like a bi-encoder's index, which is what keeps the search fast. At query time, encode the query the same way into one vector per query token. Now both sides are represented as small sets of token vectors, ready to be compared directly against each other rather than as two lonely single points collapsed from all that text. Now comes the interaction. For each query token, scan every document token and keep its single best, its maximum similarity. Each query token essentially finds the spot in the document that answers it most closely, and that fine-grained matching is where the precision comes from. Finally, sum those per token maxes into one relevant score for the document. That summation is the maxim operation. Rank documents by this combined score, and because the heavy encoding was pre-computed, the late matching stays cheap enough to serve at real scale. Strip it down and three ideas define late interaction. It keeps a separate vector for every token and matches them late. Rather than collapsing a document into one point up front, it preserves token-level detail and defers the comparison to search time, which is exactly where the extra precision comes from. It lands near cross-encoder accuracy at near bi-encoder speed. The expensive encoding is still pre-computed per side, so search stays fast, while the fine-grained token matching recovers much of the quality a full joint model would give you. It pays for this in storage and memory. Keeping a vector per token is far larger than one vector per document, and the index is more complex, though later versions like ColBERT v2 compress those token vectors to make the cost manageable. Alright, let us lock in the essentials. This approach keeps a separate vector for every token and compares query and document tokens at search time, not before, which is why it is called late interaction. It splits the difference between a bi-encoder's single document vector and a cross-encoder's slow joint reading of both texts together. Its scoring, called maxim, takes each query token's best match among the document tokens and sums those maxes into the final relevant score. This cost is storage, since a vector per token is far larger, which ColBERT v2 later compresses. If the internals of Retrieval fascinate you like this, we break down many more of them over at standarity.com. See you inside.